Okay, so again, all circles are similar, but showing unit 4 would have been a little bit tough with all the sides. So we do a similarity transformation. And that's all I want you to do. This is sometimes called a transformation proof. Okay, but it's not really a two-column proof. It is simply writing of similarity transformation. This is all it is. Okay, so here's what we're going to do. Beginning with circle N in the diagram, show that circles N and M are similar. So we're starting with this circle down here. In other words, just write down the similarity transformation. That's all we're doing. All right, so we're starting with this one. We need to move it, certainly, and we also need to shrink it. So do you want me to make it the same size by shrinking first, or do you want me to move it up there?
Shrink it first.
Okay. So that would be dilating. So I'm going to say dilate circle N. Okay, now any thoughts? We're going to have a scale factor. So what do you think we need to dilate by? There is a way to tell from the diagram. Yes?
Divide the radius by 2.
You know, it's not going to be 2, but what you said is what we should do, though. We should look at the radius of each one. Yeah, okay, yes. So we should just look at the radius and compare those. That's how we get the scale factor. Normally we look at like this side and in a triangle, and maybe it's double, or we do the ratio, and that would be the scale factor. So yeah, radius here is 3, or you can do diameter. It's going to work out to be the same, but 3 here and 2 here. So what is it? 2/3 because we're making it smaller. If we were going from the smaller circle to the bigger circle, 3/2. We flipped it. So we looked at the radii, 2/3. Now I need to say around the point, so I need to know where I'm going around. So dilate circle N by 2/3 around. Okay. Now actually, I could choose any point. I could choose the origin, and it would get smaller. It'd be 2/3 as far away. It'd be there. Or I could choose up here, and maybe the circle would be here. So I can choose any point, but the easiest one is just going to be around the center. So I think that's M. Because if I choose point, because I need to make a sketch of what this is going to look like. If I choose point N, N is not moving, that point. And so now it's going to have a radius of 2. So here's where you could use a compass if you wanted. And just draw that circle with a radius of 2. So I chose point N so it wouldn't be, I had to figure out some else, over here, which wouldn't take too much work. I just have to multiply, what is that, 5 negative 5, point N. I have to multiply it by 2/3. So it would have been over here, but it'll be easier this way. Okay, and now I can move it up. Now this is interesting, I saw earlier translate, I was just going to slide it up 10. You guys see anything else we could do? Yeah, reflect. So, it doesn't matter. You could say, I'll put both. You could say translate up 10, or you could have said reflect over x-axis. So what we've done is we've mapped circle N onto circle M, and shown that those circles are similar. So a similarity transformation. Okay, ready to move on to page 2. Any thoughts still on that one? I like that too, because it's always good to cycle what we go through. So looking back at similarity, looking back at transformations. Yes. That was the one. I guess Monday, Tuesday, or something. It becomes a circle as it goes to infinity. Yeah, any regular polygon. So flip it over and let's talk about arcs, naming them, and their angle measure. I first have to say central angle because that leads into the arc. Okay, so a couple of vocab terms here. First is central angle. It is simply an angle at the center of a circle. So as an angle, its vertex is the center point of a circle. So in this case, angle CPA, or I could say angle APC. And there's others, CPB, or even the straight angle APB. So I name it with 3 points, like normal. So that's a central angle. Let me go ahead and tell you something probably would have talked about a little bit later, but let me go ahead and do it now. Let's say this angle is 50 degrees. Okay. Now, would you agree that if I was at point P, I could do a 360 rotation around point P? So there's really 360 degrees from the inside of the circle. So the central angle, any central angle would have to be less than 360. It could be any angle measured before you get one rotation. So if that's 50, I'm going to say that this arc also has a measure of 50. So the central angle and the arc have the same measure. And so we think now that tomorrow we'll learn about arcs also have length, but for now they have measure. So just as the central angle is 360, the arc could have a measure of 360 all the way around the circle. This is the way we think of the degree of an arc. So basically for now, there's going to be other types of angles that will help us solve for this, but right now the one we know is central angles and their arc have the same measure. Only central angles. So we're going to use that in a few minutes to solve for missing angles. Now let's talk about naming an arc. So that arc that I put up there at 50 degrees is going to be CA or AC. Now to differentiate it from segments, or like a line segment, or even a line, or even a ray. A ray is just half a point, just a point, and then a line in the other direction. We're going to put curve on it. So do make sure to put that when you're naming arcs. So now, and this is pronounced arc CA. Okay, and an arc, I should have mentioned this. We've done them with constructions. We didn't always do the full circle, we just did an arc. It's the simplest definition, part of a circle. Not the whole thing, just part of it. Now there's 3 different types of arcs. You're probably familiar with this one, semicircle. That's an arc, half the circle. You're going to name it with 3 points. So semicircles you name with 3 points. You'll notice that one, CA, was different. So I could say arc ACB. I could have turned it around BCA. I just need to make sure that the endpoints A and B are the endpoints of a diameter. Right, so like this is a diameter right there, segment AB. And so I just need to make sure to put A and B on the end and have some other point in between. I could have gone the other direction, ADB. Notice how I didn't use E, so I could skip it. I could say ADB, or I could have said AEB. So don't use 4 points, don't use 2, and make sure that your endpoints of the diameter A and B are on the end here. Let's see. So don't use 4 points. Yeah. Oh, I'll come back to the angle measure here in a second. So then there's minor arc and major arc. Minor is anything less than a semicircle. So anything smaller than a semicircle is minor. And we'll use 2 points for that. That was the one I did a minute ago, CA or AC. So if it's smaller than a semicircle, 2 points. Semicircle, 3 points. Anything bigger than a semicircle is a major arc, and you'll use 3 points. So for example, I'll do CBD. There's others I could have said. There's a lot of others. A, B, C, E, C, D. As long as it's bigger than 180. And the other thing is you can go clockwise or counterclockwise when you're naming these. Doesn't matter. I know what I was going to say a minute ago. With semicircles, somebody said, well, what if there was no C here? Could you name it like AB, or what would you have to do? You have to go the other direction and say AEB. Sometimes there might be a circle and there's just what's its diameter. If you really wanted to name this semicircle and there was no point, then you have to add one in. So you'd like add in C and then you could call it ACB. Okay, any thoughts on naming the arcs? 2 points is the only one for a minor arc. Okay, so then they actually have as I was mentioning here, right? They have measure at the 50. So semicircle is 180, half the circle, circle 360. And then a lot of what we'll do is find minor and major arcs and their measure. So for now, that's what we'll do. And minor, you're pretty much going to use the fact that a semicircle is 180 and a full circle is 360. And you'll be able to add and subtract other measures from that. The one thing we do know is that for a minor arc, it's got to be less than 180. Because it's less than a semicircle. And a major arc has to be greater than 180 because it's bigger than a semicircle, but it's less than 360 because it's not a full circle. Okay. With that knowledge, let's go ahead and here's what I want you to do is you're going to try examples 1, 2, and 3. I'm going to give you about 2 minutes on each, and just keep going. But after you're done with this one, move on to example 2, and then after about 2 minutes, I'll go over example 1. Then I'll go over example 2 and then example 3. So for example 1, circle O. I'll give you that one. How about somebody tell me a minor arc? Let's go. Okay, that's sure. Thank you.
Arc AD.
You said arc too. What'd you say? AD?
Yeah.
Oh no. You said AD. Oh.
What?
I was like, yeah, there is no T. Nice. Make sure you put the arc DA will be good. AC, CA, CE, EC, D, ED. I might have gotten all of them. Semicircle. Joe, you want to tell me one of those? Say it again. Oh, DAC. DAC, yeah. I think it's EAD. I was going to say that was just the wrong order. Yeah, as is, DAC is good. Major arc, Eli?
CDA.
Yeah, nice. That's a good one, CDA, because if you did the wrong order, CAD, that would be a semicircle. But CDA is a major arc. Any thoughts on those? Okay, so let's keep moving to example 2. Again, it's just going to be, this is a combination of adding and subtracting, and you start with semicircle as 180, edge circle 360, and also, as we'll see in part A, central angles in the arc. So what would you put for A, measure angle BB? Abby, you want some of that one?
90.
Okay, nice. So, I do just want to point out for this one, this was using central angle as 32, then saying, well, that's the same as the arc. The arc will have the same measure. And then combining these two. You also could have put the 58 down here, but they didn't ask for B, OD. So you add them together, you get 90. Nice. Okay, what about B? It's the fastest handwriting ever. Yes.
180.
Yes, it's ABC is a semicircle, so 180. I'm gonna have a question out, and it was being raised up. Nice. What about C? Somebody else? Yeah.
48.
148. Yeah. So I think this one you start with the 180 as a semicircle, but then subtract off this, right? The 32. Yeah. So a lot of these are just a little arithmetic, but knowing the puzzle, like where you have to go and start. What about DAB? Yeah.
270.
So did you start with 360?
Yeah.
Because you also could have found this one by starting here and subtracting and adding them together. Or just the whole circle is 360, and you can subtract off the blue arc, which was 90. Okay, very nice. So that's the start. Now, as we move along, there will be a couple other types of angles and arcs that we'll deal with. But for now, this is it. Doing this and knowing central angles and their arcs are the same. But we'll continue this a little later. We've got two more examples to finish up. We good so far, 1 and 2? Okay, I am going to start us off together on example 3. Can you make sure you have a calculator? Because I want you to try this one on your own. What happens is we just set this one up, and you might set up all right, something happens with the work when you put it in the calculator. All right, so the circumference of a circle is 8. So this one's actually relying on what we did last time with circumference formula. So if we look back at page 1, this is also, we got the circumference formula. This is also on the formula sheet. I'll mention here in a minute, yes, you could have done pi d on this one, but again, I just do 2 pi r because that's the formula they give us. So find the radius and diameter. So this one starts off just, you know the circumference is 8, and so you're going to plug that in. Okay, so we get 8 equals 2 pi r. And then you can get the radius from this by dividing both sides by 2 pi. By the way, use the pi button for this unit. And actually, I think in general, if you ever have to do pi, use the pi button, not 3.14. Okay, so just put that in, and then I'm going to get answers in a second here. Usually there's two different things we get. Oh, just round in the nearest hundredth. This will be again on a test or quiz. I'll tell you what to do. So 8 divided by 2 pi. What did you get? Sarah? 12 point, yeah, like 5, 6. Some of you probably got that. Anybody else get something different? What did you get the first time?
I just divided it by parts.
Sure. So this is a radius again. Anybody else get something different? Yeah. Yeah. So those are the 2 answers I generally get on this one. Did you get one of those by dividing?
Yeah.
Which one should we throw out? Which one doesn't make sense? Because the circumference is 8, and this is supposed to be the radius. Yeah. The radius cannot be bigger than the entire circumference. So do you know what happened on the 12.56? Anybody? What was it? Oh, it's 8. Yeah, that's it. It was the parentheses. Well, here, if you just did this, your calculator is doing 8 divided by 2 times pi. It's kind of weird that it does that. 8 divided by 2 times pi. When really it should be doing 8 divided by the entire expression, 2 pi. And you can see you've got 1.27. Now, ways around this, if you have a graphing calculator, you can hit alpha F1. So you're looking for the green F1 up here. You hit alpha y equals. And then these are your fractions. You just do the first one. It'll be a fraction bar. If you have the new calculators, it just has the fraction bar, right? Or even some of the scientific calculators just have a fraction bar. But are we good on that one? I want to make sure if you have the graph calculator, you know that for fraction. Alpha F1. Okay, because there is no other fraction bar. Alpha and then F1. Okay, so here I could do it here, 8, then put in 2 pi, it'll work just fine. Okay, the other way that it will work just fine is if you use Desmos. Okay, so remember, you can always use Desmos in here or on the state test. And that will automatically change it to a fraction. And then it will be like this. So 1.27 is the right answer. the other thing you're going to notice me doing from time to time here is I'm going to put about equal to, because we rounded. It's not really, it's 1.27 ... 32. Okay, so it goes on. So you're going to see me use about equal to. Okay, and then the diameter is double the radius. So if I just times that by 2, I get 2.54. Now, last thing I'll say about this one is, okay, you also could have used this formula for circumference. And this one would have been good in this case, just dividing by pi. It would have saved you from the parentheses in the 2. However, again, the formula they give us is 2 pi r, and we'll generally use that one a little more. And we'd also see this issue come up later if we didn't see it now. So I wanted to make sure. Use parentheses or just use the fraction bar. Okay, we'll do one more. Any thoughts on this one? This one. Yeah.
I already had my hand
Sorry,
up.
no.
You asked that.
Oh, I see. Good reasoning. So last thing I want to do, constructions. Remember when we found the center of the circle? We did a chord. Do you remember when we did? Okay, when we did chord and we did a perpendicular bisector, and then we said that segment goes through the center. Well, here's the theorem that backs it up. I'm actually going to say the converse of that one first, and then that one. So here's the theorem. If you have a circle, and you have any segment coming from the center, it could be a full radius, it could be a full diameter, or it could just be a segment that starts coming from the center. If you know that's perpendicular to the chord, so it's perpendicular, here's the chord, then it bisects the chord. And its arc, actually. So if this went further through, we would know that it bisects, and those arcs have been bisected. Okay. So if you have a segment from the center and it is perpendicular, then it bisects. Now the converse theorem is the one we use with constructions. In a circle, the perpendicular bisector of a chord. So that's what we did. We did a chord, we did perpendicular bisector, and what we know is it goes through the center. That's the theorem. And that's the converse, the reverse. So, to finish up here, let's find x in this diagram. So that segment is x. Not the radius, well, that's the x they're looking for. It's perpendicular to this chord, and since this chord is 12, it's going to bisect. That's something else I should point out. I don't think we've seen this before. If they put a number or a variable right in the center, it's referring to the whole segment. So, for example, 15 is referring to the diameter, not the radius. And 12 is referring to the entire chord, not just part of it. Okay, they would clearly, they'd write 15 over here if they meant the radius. Okay, so since this is perpendicular, it bisects the 12 into 6. So 6 and 6. All right, so it boils down to this. We're finding x in that right triangle, and this is 6, and this will be 7.5, half the diameter. Okay, so we use the properties of circles, and we get a right triangle equation. And we can do Pythagorean theorem. X squared plus 6 squared equals the 7.5 squared. So we get x squared, and we get 36, and then here, let's see, 56.25. So I subtract 36 from both sides. Now let's see, this will be 20.25. Okay, and finally a square root, and that will get us 4.5. Yeah, 4.5. All right. Well, that's it for arcs. So we talked about naming arcs, minor, major, semicircle. Central angles and arcs have the same measure. Circumference, and then one last example with really a theorem we've done before with constructions, but just using it more fully now. Any other thoughts, things I can answer?